Steinhauer here. Welcome back. We're continuing our discussion of how the sun generates energy in its core. And we've already gone through the steps that are required to fuse 4 protons into a helium-4 nucleus. The question that remains now is, how does that actually give us energy out? So we need to understand some things about mass before we can really answer this question. So I'm here to tell you, you may not know, the mass of a proton is this number, 1.6726 times 10 to the negative 27 kilograms, which is a very small number. Obviously, a single proton does not have much mass. But the interesting question is, what is the combined mass of the 4 protons that make up, that went into making that helium-4 nucleus? And if you just take that number and multiply it by 4, you get this number. The mass of the 4 protons, 6.690 times 10 to the negative 27 kilograms. Right, so what is the mass of a helium-4 nucleus? Well, the mass of a helium-4 nucleus is this number, 6.643 times 10 to the negative 27 kilograms. So that's interesting. The mass of a helium-4 nucleus is less than the mass of the 4 protons that came together to create it. And so there's a difference here, right? You've lost some mass in going from 4 protons to 1 helium-4 nucleus. Some mass was lost. How much? Well, you just have to subtract these two numbers. Subtract those two numbers, and you get a difference of 0.047 times 10 to the negative 27 kilograms. So it turns out that that is an important number because that mass cannot just go away. In fact, you may remember some of our conservation principles in physics from earlier. One of the more important conservation principles in physics is conservation of energy. Energy can neither be created nor destroyed. It can only change form. And so how does that relate to mass? Well, there was a guy that you might have heard of by the name of Einstein who realized in the early 1900s that energy and mass were equivalent. And he wrote down a famous equation which represented the proportionality constant, which represented the equality between these two. And you've probably heard of this formula. It is E equals mc squared. What does this formula tell us? It tells us that mass and energy are related. And how are they related? The proportionality constant is c squared. Let me just define all of these terms. E equals energy. M is mass. And c is our old friend, the speed of light. So Einstein realized that you can convert matter into energy and energy into matter, and that they all encompass a conservation of energy. So if you lose some mass, it has to be created into energy. You can lose some energy and have it be created into mass also, if you like. And the proportionality constant is c squared. If you want to know how much energy you get out of a single element of mass that gets destroyed, multiply that mass by c squared, and that will give you an energy in joules. Okay, so that's an exciting formula, and we get to use it now to determine exactly how much energy we get when we take 4 protons and turn them into a single helium-4 nucleus. So it's not the total mass of the helium-4 nucleus. We don't get all of that energy out. We only get the mass that was lost, the difference in energy that we calculated in the previous slide for how much mass is lost when you turn 4 protons into a helium-4 nucleus. So let's go ahead and work this out. We know E equals mc squared. We know, we know that mass is, let's just write them over here, 0.047 times 10 to the negative 27 kilograms. C, we know, is about 3 times 10 to the 8 meters per second. C squared, if you don't remember how to do this, it's not that hard. to square a number in scientific notation, you just square the base and multiply the exponent by 2. So 3 times 10 to the 8 squared is 3 squared, which is 9, times 10 to the 8 doubled, or 16. So c squared is 9 times 10 to the 16. It has units. You have to square the units too. It has units of meters squared per second squared. So we can plug both of these numbers in now to our formula over here. E equals m 0.047 times 10 to the negative 27 kilograms times c squared, which is 9 times 10 to the 16 meters squared per second squared. Okay, multiply those two numbers together. You get 4.23 times 10 to the negative 12 kilograms meters squared per second squared. And if you remember, a kilogram meter squared per second squared is a joule of energy. So this gives us 4.23 times 10 to the negative 12 joules of energy, converting 4 protons into a single helium-4 nucleus. Is this a lot of energy? No, it's a very small amount of energy. It's an extremely small amount of energy, right? A 60-watt light bulb gives off 60 joules of energy in a single second. This is enough energy to power a 60-watt light bulb for about 10 to the minus 13 seconds. So how can this possibly power the sun? Well, the answer is not in quality. The answer lies in quantity. This must be happening an awful lot in the center of the sun. How often must it be happening in the center of the sun? We know that the luminosity of the sun is 3.8 times 10 to the 26 joules per second, or watts. It's a 3.8 times 10 to the 26 watt light bulb. So if the sole source of energy is hydrogen being converted into helium, how often does this reaction have to take place in the center of the sun to explain the luminosity? The answer is a lot. We know that L is energy per second. And we know the energy per reaction, which we calculated in the previous one. If we want to know reactions per second, we just have to divide these two numbers. So our 3.8 times 10 to the 26 joules per second divided by 4.23 times 10 to the negative 12 joules per reaction. The joules cancel out, and we get a number that is about 9 times 10 to the 37 reactions per second. So the per second is still on the bottom. The reactions is in the denominator of the denominator, so it moves up to the top, and the units on this are exactly what we want them to be, reactions per second. 9 times 10 to the 37. That's almost 10 to the 38. That's a 1 with 38 zeros after it. Let me just try to write that number out so you can see how big a number this is. Well, I'll actually do 9 times 10 to the 37. So that's a 9 with 37 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. That is the number 9 times 10 to the 37. It's a ridiculously large number. It's a number that's so big you can't even fathom it. I can't even imagine a million, much less a number that's 10 to the 37. It's just so big. So it isn't that this particular reaction gives us a huge amount of energy. It's that there's so much hydrogen in the sun, and it's happening so much per second, that it can give us an energy that is this big for the total sun itself. So here's a question for you. You can try it if you want to. How much mass is converted into energy every second in the sun in kilograms? You can pause it and try it out for yourself. Okay, let's go through it together. Again, this is an E equals mc squared problem. In this case, we know how much energy is being generated. How much mass is there being converted directly into energy every time? Well, this is just E equals mc squared. This is really energy per second, but we want mass per second. So you can just ignore that mass per second. They're both in there, but they're just gonna be along for the ride basically. So in this case, we know what E is, and we want to know what M is. So we're going to take this E. Let's just do some algebra first and solve this thing for M. We can divide both sides by c squared. The c squareds cancel out over here, and we're left with M equals E over c squared, which is equivalent to E equals mc squared. So we know what these two numbers are. The energy from the sun every second is 3.8 times 10 to the 26 joules per, I'll leave the seconds in here, joules per second, divided by c squared. We know that's 9 times 10 to the 16 meters squared per second squared. We get a number that is 4 times 10 to the 9. And the units on this, we have to actually write them out if we want to do this directly. A joule is a kilogram times meter squared per second squared. So the meter squared goes away, the second squared goes away, the joules we just replaced. This is kilograms per second. So every second in the sun, you must destroy 4 times 10 to the 9 kilograms worth of mass and convert that directly into energy. That's a lot of mass. A metric ton is about 10 to the 3 kilograms, 1,000 kilograms. That's 4 million metric tons of mass being lost by the sun every second, converted directly into energy. This might seem like a lot, but the sun has a mass of 10 to the 30th kilograms. So this is a small drop in the bucket of even the amount of mass that's in the core of the sun itself. You'll have a homework assignment on this week's Kappa where you have to figure out how long the sun will last given this amount of energy generation and this amount of mass loss. And it turns out that it is a number that is comfortably larger than the current age of the sun. So that's a good thing. Okay, so that's how it gives us energy. Basically, it's converting mass directly into energy at the center of the sun by doing this nuclear fusion process. And this, by the way, is an incredibly important thing for us here on Earth. If we could figure out a way to do nuclear fusion like this on the surface of the Earth, it will solve completely all of the world's energy problems because there's so much hydrogen available to us on the surface of the Earth. In fact, all water is made up of oxygen and hydrogen. We could potentially make energy just from dissociated water. It's a very exciting prospect. People are working very hard to make it happen. People have been saying it's about 20 years out for the past 30 or 40 years now. We're still saying it's about 20 years out, but real progress is being made. The largest laser facility in the world is in California at Lawrence Livermore Laboratories, and their sole purpose, the National Ignition Facility, is to try to figure out how to do this on the surface of the Earth. It's an extremely difficult problem. We've gotten fusion to work. We've managed to successfully turn hydrogen into helium, but it takes so much energy to make that happen that we haven't been able to recover that much energy from the reaction after it's happened. So we know how to do it. We just don't know how to do it in a sustained way such that the amount of energy we get out is more than the energy we're getting put in. If we can solve that problem, then the world's energy problems are just solved. So keep an eye on that. That's an important thing in the next, hopefully 20 years, we'll see. Okay, so that's exciting. We know what powers the sun now. One more topic I want to cover in this chapter, and that is talking about how things that we observe don't always match the theory, and why that's important, and what it means for science. So you might remember, let's talk briefly about the solar neutrino problem. You might remember in the previous video we talked about the steps that must be undergone in order to convert hydrogen into helium, the proton-proton chain. As a part of that chain, every time you turn hydrogen into helium, you generate 2 neutrinos at the center of the sun. And those neutrinos interact extremely weakly with matter. They basically come streaming out of the sun. So we know exactly how many times this reaction happens per second. We just did the calculation. We know how many neutrinos should be streaming out of the sun. If we can detect those neutrinos, we can directly test our theory about whether this is actually what's going on in the sun. And people designed an experiment to do just that. You don't take our word for it that something is the way it is. You always make a test. You can design a test to test your theory. You do it. Hopefully you're right, but maybe you're not. And so that's what happens. They designed this experiment. You see the huge tank here. They filled this tank with 100,000 gallons of perchloroethylene, which is a common dry cleaning chemical, mostly chlorine. And it turns out that although the neutrinos are streaming actually through our bodies and every part of Earth all the time, a huge number of them, something like 10 to the 11 per centimeter per second, but they don't affect us because none of them stop in our bodies or much of anywhere. But if you have enough of this stuff, it turns out if you do get a reaction where one of those neutrinos happens to interact with something, it will turn that chlorine into argon, right? And so they just set this vat there and let it sit there for a month. And then they were able to use some process to collect all of the argon atoms that have been created in this vat and count them and see how many that they had at the end of a month. They expected, based on their understanding of how this physics worked and how the neutrinos would interact with the chlorine atoms and how often they should do that and how many were coming through, that they would get about 6 reactions per day. They would make 6 argon atoms per day. And when they did the first bubble up, they found that there were only about 2 per day that they had discovered. They did another month, and a whole year went by, and they were consistently getting 2 reactions per day, which is a factor of 3 smaller than they were expecting. They're expecting to see about 6 per day, and they actually saw about 2 per day, a factor of 3 not worse, but lower than they were expecting. So this became known as the solar neutrino problem. And it's a real problem. There was something we didn't understand about the physics. Either we didn't understand how the sun worked and how nuclear fusion worked, or we didn't understand something about how neutrinos interacted with chlorine, or we didn't understand something about neutrinos themselves. And this you may think that this is a huge problem, and it was a huge problem. It's also a huge opportunity. And in fact, when I was sitting in college taking my first astronomy class, we had a speaker come in and give us a talk about the solar neutrino problem, which hadn't been solved at that point. It has now. And he didn't phrase it as the solar neutrino problem. He phrased it as the solar neutrino opportunity. This was an opportunity to learn more about the universe, to correct something in our theory that isn't quite right. And that's a huge thing. If you can make your theory better and better match reality, that's a huge opportunity for you to learn more about the universe. And so one possibility is that we didn't understand how neutrinos interact with chlorine. So they built other neutrino detectors. This is Super Kamiokande, a neutrino detector in Japan. This is a picture of some workers cleaning every single one of the thousands and thousands and thousands of photo multiplier tubes that are on the edge of this detector. So this detector is much bigger than that chlorine tank, and it uses purified water to do the detecting. And the cool thing about this is not only can you detect every now and then a neutrino that happens to interact with one of your water molecules, but it will emit a flash of light when that happens. And if you can trace the path of that flash of light, which you can with these tubes on the edges, you can trace back to where that neutrino actually came from to see if they're coming from the sun, for instance. So this is a completely different way of detecting the neutrinos, and yet they also found a factor of 3 smaller than they were expecting to see. So it wasn't our understanding of how neutrinos acted with chlorine. It had to be something else. So what is the solution to this problem? It turns out that the thing we didn't understand all that well was the neutrinos themselves. It turns out we knew this before, there are actually 3 varieties of neutrinos. There are electron neutrinos, there are mu neutrinos, and there are tau neutrinos. What we didn't know at the time was that these different flavors have mass, and they have different masses, and that fact that they do have mass says that as they travel through matter, specifically the sun or other matter, they can spontaneously change flavors. So an electron neutrino can become a mu neutrino can become a tau or an electron neutrino, and in fact, you can move from any one of these vertices to any of these other vertices spontaneously. So they can change flavor. Now, it's only the electron neutrinos that are created in the center of the sun. These kinds of neutrinos are more exotic and aren't produced in these kinds of reactions. And it's also only the electron neutrinos that are detected by our chlorine and water-based detectors on Earth. And so the fact that we were a third lower, we were 3 times lower than we should have been, makes sense if those electron neutrinos that were generated in the surface of the sun, in the center of the sun, have spontaneously changed flavor several times on their way out. We expect, after enough of these transitions happen, that about a third of those neutrinos will be electron neutrinos, about a third will be mu neutrinos, and about a third will be tau neutrinos. And so the fact that we're only seeing a third of the expected results is exactly what we should be expecting if these flavor switches happen. And so we can explain it by the spontaneous changing of neutrino flavor for these electron neutrinos. So that's an exciting thing because it shows a couple of things. You know, people think that scientists are always just trying to prove their theories right. And certainly it's nice when you're right, but it's even more interesting when you're wrong, because that points the way usually to new and greater physical insight as to how the universe works. And that's really the way science progresses. It's not the victories, it's the failures that allow us to make progress and understand and gain a deeper understanding of the universe as a whole. So that's my soapbox moment for the day. All right. Anyway, that's all for this section. We'll come back in the next section and talk about the way the sun is structured and how the surface of the sun works and some processes that are going on in other parts of the sun besides the core. Okay, see you then.